Last time we worked out the contrast transfer function for a sinusoidal grating, and I promised you that if we know the transfer function for sinusoidal gratings, we can get the transfer function for any sort of image. Well, that's a 2D problem, but today we're going to do the simpler 1D problem first. The Fourier transform, the basic idea was discovered by Joseph Fourier. He was governor of Grenoble, but in his spare time, he worked on solving the heat equation, and he found that he could solve it more easily if he decomposed the temperature as a function of position into sine and cosine functions. So we're going to do the same kind of thing today. So here, for example, is a function. This is a Gaussian. And we are going to try to approximate it by a sum of cosine functions. So here's the first cosine function, and here I have it superimposed on the original. Here is the second term. This is a cosine with twice the frequency. There's a cosine with 3 times the frequency, and you can see that this blue curve is getting close to the dashed line, which is our goal. 4 terms, 5 terms, 6 terms. So 6 terms, we've reproduced the original function to a part in 10 to the minus 5. And this is actually a very powerful idea. I could give you a function, I could tell you its value at thousands of points along the x-axis, or I could just give you these 6 or 7 coefficient values and tell you this is what my function is described as. I can just give you those coefficient numbers. But where did I get those coefficient numbers so that I could scale these different cosine waves by the correct amount? Well, I got it from the Fourier transform. In fact, the Fourier transform is an operation that converts a function, let's say, of x into another function that's a function of u. And this function of u gives us the coefficients. So for example, the coefficients I used in that last example are indicated by the dots on that curve. Okay, so what is the Fourier transform? Well, it's a big integral. It's an integral from minus infinity to plus infinity. And what it does is it takes a function g of x and converts it into a function big G of u. And the way it does it is it takes an integral over all x values of the original g of x times this complex exponential, e to the minus I 2 pi ux, and integrate it over all x values. And I can recover the original g of x by doing the inverse Fourier transform. So I plug in g of u, and it's almost exactly the same formula, except that the exponent here, it has a plus sign instead of a minus sign. So let's do an example. And the example I'm going to start with is this Gaussian function. As you'll see, it turns out to be a particularly elegant case. So I'm going to let g of x be e to the minus pi x squared. So that's our Gaussian function. And we want to know what g of u is. Well, g of u is given by this formula, and so I can write it down explicitly. So g of u is going to be this integral over all x values, g of x e to the minus I 2 pi ux dx. And this is our friend, the complex exponential, which I hope you're getting comfortable with. We'll expand it here. So this is the same as g of x times cosine of 2 pi ux plus I times sine of 2 pi ux. And there's a minus there, but I'm not going to bother putting a minus there because cosine of x and cosine of minus x are the same. So just out of laziness. I'll not put a minus sign there, and this is integrated over all x. So what does this integrand look like? Well, here's my original function, g of x. It's this Gaussian function. It's kind of, it goes to 0 around between -1 and 1. So this is g of x as a function of x. And what I want to do is I want to multiply it by either a cosine function or a sine function. So for example, here's a cosine function. And here's a sine function. Trying to get those in correct phase. That'll do. Okay. So that's the sine function. And this one is cosine function. And so then there's a simplification hiding here, which is, turns out that because g of x is an even function, I'll try to draw it a little bit more carefully. One of these two, the sine or the cosine, is going to integrate out to 0. Because what we're doing is we're taking this symmetric function and we're multiplying it by either a symmetric function, an even function cosine, or an anti-symmetric function, that is an odd function, the sine function. And I think you can see that the sine function, which spends as much time being positive as negative, is going to average out to 0 when it's multiplied by this even function. So we can ignore this part. And so finally, what we really need to do is to do this integral. G of x cosine 2 pi u x dx. And this is what g of u is. So what does this look like? So what I do is I take a cosine function like this, I multiply it by my Gaussian g of x, and then I add it all up, take the area under the curve, and do the integral. So I've done this on the computer, and here are some examples. So there's my g of x. Here is the value at u equals 1 of this cosine 2 pi u x. So you can see u is setting the frequency with which the cosine oscillates. And so I just multiply those two together, and I get this white curve. And just to guide us, I've also put in a dashed curve the original function. So I integrate the area under this, and I get something like 0.8. It turns out that the area under the original g of x is exactly equal to 1. So then I start increasing the frequency. As I go to higher and higher frequency, you can see that I'm beginning to get peaks and valleys from the cosine function showing up in the product. And so this whole product is then going to integrate out to a much smaller value. And if I go up to really fast, really rapidly oscillating cosine functions, you can see that this thing averages out to something very close to 0. So what we've done here is we have obtained values of g of u at 1, 2, 3, 4, 5, and so on. And it starts out at 1, and it gets smaller and smaller and smaller, and gets really vanishingly small as we increase the value of u. Now, it turns out that I can also evaluate this for negative values of u, and that's easy because when I flip to a negative value of u, the cosine function being even gives us exactly the same result, and so we're going to get exactly the same result out of the integral, and so we will get symmetrical points here, and the final result looks like this. Looks a lot like the original function. So we can do calculus, and I just invite you to look this up in the notes if you care about it. So this is the integral we wanted to do. We can play with the exponent because these are both exponential functions. We can complete the square in the exponent and pull out the extra term. And then it turns out that this integral that's left in there is equal to 1. And so the final result is that g of u is e to the minus u squared. Minus pi u squared. So this is a really lucky situation. It turns out that you don't know yet that it's a lucky situation, but it is a unique situation in that we started out with a g of x that has this form. It's a Gaussian, and its corresponding g of u has the same kind of form. It's a Gaussian. And with this, I'm going to start building up a table of Fourier transform pairs. That is, we're going to find the g of u that correspond to particular choices of g of x. And so this is our first pair, e to the minus pi x squared gets transformed through the Fourier transform to e to the minus pi u squared. And this is a unique situation. It's also very nice in that it only takes a few terms. It only takes a small number of points to describe a Gaussian function like this. And the mathematicians say the Gaussian has a sparse representation in the basis of Fourier series. Okay, so let's try another function to start with. This is my new g of x. It's called the rectangle function. It's a function that is 0 everywhere except on this interval from minus a half to plus a half. So it's a rectangular pulse with area unit equal to 1. And so now we can do the same kind of trick here. We'll put in a cosine wave of frequency 1, there it goes. I put in a cosine wave of frequency 2, and it turns out that the proper coefficient to use there is 0. Here's adding the wave with frequency 3. That's this blue curve, and you can see that the blue curve is now beginning to approximate the square edges and the flat top of the rect function. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I decided to stop at 10 terms, and that with 10 terms we have this white curve, which you can see is not approximating the rectangular function all that well. This is a problem because we're trying to approximate a function that has a discontinuity here by the sum of very smooth continuous sine or cosine functions. And that intuitively is why the approximation is not so good. Now, if we do the Fourier transform, we can see why we have this funny problem. So I take the rect function, put it through the Fourier transform, and here are the points representing the coefficients that I plotted in the last picture. And you can see that g of u oscillates. It oscillates around 0. Every other point actually has the value 0. And it keeps oscillating on and on forever. So it does not converge all that well. So we can evaluate that function. I'll just have you look at the notes to see how you do the integral. But the result is this, that if g of x is what we call the rect function, then g of u is sine of pi x divided by pi x. This is a special function that goes by the name of the sinc function, and it has this oscillating behavior where there is a 0 at u equals 1, u equals 2, u equals 3, and every integer value of u, there is a 0 in the sinc function, and in between it oscillates in polarity. And it oscillates for a long time because you can see that as x becomes large, this shrinks only as 1 over x. So that's our second Fourier transform pair. Here I'll just say that the rect function transforms to the sinc function. I'll write it out, which is sine of pi x divided by pi x. Okay, so along with telling you some Fourier transform pairs, I'm going to tell you some Fourier transform properties. Because if we know a few Fourier transform pairs and we know a few Fourier transform properties, we can actually do a whole lot of things, as we'll be seeing later in the class. So the first property is to say that if I have two functions, I'll call them g of x and h of x, and I add them together, the Fourier transform is going to be what? Well, the Fourier transform is a linear operation. We're just taking an integral, and so the sum of these two integrals is going to be the same as the integral of the sum, and so the Fourier transform of the sum of these two is the sum of these two. And this is a property that I will call linearity. Another property I want to talk about is the scaling property. Let's do an example. Let's suppose that I'm now plotting my g of x as a function of x. And this is my old Gaussian function. This is my e to the minus pi x squared. And now I'm going to have a new function that is going to be narrower and sharper. So it's going to look like this. And my g of x in this case is a times e to the minus pi ax quantity squared. So what does this do? This a here means that it's a times taller, and this a here means that it's a times narrower. So what is the Fourier transform of that going to look like? Well, we can sort of figure that out from what we've seen in trying to do the integral numerically before. So the area under this red curve, well, all right, so first let me just put in the dots for my usual function, e to the minus pi x squared, and we get this, and this is e to the minus pi u squared. Now, what's going to happen when I have this narrower g of x? Well, now if you remember, what we're doing is we're multiplying by this oscillating cosine wave and summing it up. And you can see that the cosine wave can be oscillating a whole lot faster, and we still get a substantial value out of this integral. And so it turns out that the final result is that the corresponding g of u is a lot broader. And so I'll just draw it in like this. And the result that I'm giving without proving to you is g of u is equal to e to the minus pi u over a squared. So let's go ahead and derive this. So g of u, we know, is given by this integral g of x e to the minus Okay, so let's figure out where this formula comes from. So g of u, we know, is going to be this integral of g of x, a e to the minus pi ax quantity squared times cosine of 2 pi u x dx. And we're done with this drawing. And we can do a substitution. I'm sorry, this is du. I'm sorry, this is dx. We're integrating over x. So what we can do is we can change the variable of integration. We can let y is equal to ax, and then dx is equal to dy over a. And so when we do this substitution, then we have g of u is equal to a e to the minus pi y squared times cosine of 2 pi u y over a times dy over a. And you can see that the a's are going to cancel. And we could say that this is just the same as 2 pi u over a times y. And that's the only place where u appears in this equation, so that we finally see that g of u is going to be the original g of u, but with u replaced with u over a. So it's going to be this. It's going to be e to the minus pi u over a quantity squared. So we have now a new Fourier transform property, and this is called the scale property. And the scale property says a times g of ax, so I make the original function narrower and taller, and its transform is going to be g of u over a. That is, I make its Fourier transform broader by this same factor. So that's the scale property. Now, let's kind of take this to an extreme. So let's make this function even taller and even narrower. In fact, what we'll do is we will say, let's let g of x is equal to the limit as a goes to infinity of a e to the minus pi times ax squared. Let me write this a little clearer. A e to the minus pi ax quantity squared. So what happens is a gets larger and larger. This function gets taller and taller, and we're starting to get functions that are really narrow and really tall as a gets bigger and bigger. And in the end, we have a function that is so tall that its peak value is infinite and its width is infinitesimal. And this is a very famous function that's called the Dirac delta function, delta of x. And the delta function has some really cool properties that we're going to make use of. But before we do that, let's think about what is the Fourier transform of a delta function. Well, if we look at the scale, what it says is that if we're taking these functions and computing their Fourier transforms, here's what they look like. Here's g of u as a function of u. And so here's my original one. It's one of these Gaussians. Here's the broader one I get when I made a somewhat larger. And as I'm going to this limit and making it sharper and sharper, this expanded Gaussian becomes flatter and flatter, such that it turns out that from the scale property, we can deduce that delta of x has the Fourier transform 1. That is, the Fourier transform of the delta function is a constant function, and it's everywhere equal to 1. Okay, properties of the delta function. And I'll put those. I'll make a little. I'll make a little table over here. So delta function properties. Well, delta at anywhere, delta of x, where x is not equal to 0, is 0. So the delta function is 0 everywhere where its argument x is not equal to 0. Delta x is infinite when x is equal to 0. And the area under the curve of the delta function is equal to 1. So I can say that the integral of delta of x times dx, and let me write a delta here, this is equal to 1. So that is the total area under this spiky function. Looks like that. And there's one other cool property that we may use the next time or two, and that is the following property. If I do an integral, delta of x minus b times some function of x dx, the final value is equal to f of b. Now, how does that work? Well, this is a delta function that is displaced somewhat from the origin. So delta of x minus b is a delta function that is just centered on the point x equals b. And if I multiply this by another function, I'll call this f of x, then it turns out that the only time when this integrand is not 0 is at the point where x is equal to b. So if you do that integral, what you get back is exactly that value of our original function, x, and this is f of x. So that's where this formula comes from. The delta function allows us to pick out the value of a function at a particular point. Okay, we're almost done with our table of Fourier transform properties, except that I want to talk about the shift property. And so we'll do an example of that. So the question is, if I have a function g of x minus b, so I've taken my function and I've shifted it over. For example, I take my original Gaussian function and I shift it over like this, centered on some value b away from the origin. So this is x, and this is g of x. Then what is its Fourier transform? What is g of u? Okay, so we can work that out. So g of u is equal to our old friend, the integral g of x minus b e to the minus I 2 pi u x dx. And again, I can just do a change of variables trick. So in this case, I'm going to let x prime be x minus b. Dx is the same as dx prime. And so this is exactly the same integral, except that now I have g of x prime e to the minus I 2 pi u times x prime plus b, all times dx. So it's almost exactly the same, except I've got this b up here in the exponent. So now what I'm going to do is I'm going to separate the exponential function into two parts. And one part is not going to depend on x, so I can take it entirely out of the integral. And so this is what it looks like. I have g of x e to the minus I 2 pi u x prime dx prime. The integrating variable is dx prime, and that's an x prime also. And this is all multiplied by e to the minus I 2 pi u b. So I took the b term out of here, and I made a whole different exponential out of it. And so we know this guy. This is our old friend, big G of u, that is the that's the original Fourier transform of g of x. And then this is an extra term. This is that's a complex exponential. So the property here, this is the shift property, says that if I have g of x minus b, its transform is g of u times e to the minus I 2 pi u b. So here are my two original functions, and here now are the Fourier transforms of those. So here's g of u as a function of u. And I know in the original case, my original Gaussian centered on the origin just gives me a Gaussian centered on the origin. I'm going to make it plot it wider here, as you'll see in a minute. So let's suppose that it looks like this on the scale that I'm plotting it. Okay, so what about this one? If g of x is equal to this shifted function, what's the situation? Well, it's exactly the same. It's the same g of u, but it's multiplied by this complex exponential. This complex exponential is periodically changing with frequency b. And so if I have a certain degree of shift, what happens is that this function that was normally real becomes a complex number that is oscillating. And so if I tried to plot it in 3 dimensions, what I would see is this oscillation, this complex exponential going from real to imaginary to negative real to negative imaginary to imaginary. And so this becomes a sort of spiral whose envelope is equal to the original Fourier transform of the Gaussian function. So with that, we've defined some Fourier transform pairs, and we've worked out a few Fourier transform properties. And I don't think that you can really make good use of mathematical concepts like this unless you do something with them. So, I've made up a little homework problem. So the homework problem is this. Let's suppose that our g of x is actually just the sum of 2 of these Gaussians. Each one is displaced by 2 units from the origin. And I want to know what g of u is. We'll talk about the answer to this next time. So see if you can work this out. This you can do just making use of the linearity and the shift properties of the Fourier transform. So as a summary, these are the things that we've learned. Here are Fourier transform pairs. Here are Fourier transform properties. And these are the properties of the delta function.